Good evening all. In today's session, we are going to see this small derivation, that is a radio communication link FRIIS transmission formula. In the previous session, we have already discussed the maximum effective aperture and the directivity for two practical antennas. One is short dipole, the other one is half wave antenna. And one more antenna parameter we have seen, that is effective height. Just like the effective aperture, as it is always less than the actual aperture of the antenna, even effective height will also be the same. Actual height of the antenna will be more, effective height from which we will get the output, that will be always less than the actual height. Then we have seen the relationship between AE and H, effective height and the effective aperture. So in today's session, we will be discussing regarding the FRIIS transmission formula. In other words, how this can be asked is, derive the relationship between input power and the output power in terms of apertures. Okay, instead of giving you derive the FRIIS transmission formula or derive the radio communication link formula, the question may be twisted in this way: the power, input power and the output power in terms of apertures and the distance between the two antennas. This can be the question. Let us start. FRIIS transmission formula, it is used to find the power received by the antenna. In order to get this equation, let us consider this setup. You can see it on the screen. We have a transmitter here, a receiver, then antenna is connected to it. See, an outward material is connected here. It is having the aperture, transmitting material, that is transmitting antenna is having the aperture AET, effective aperture of the transmitting antenna, and AER is the effective aperture of the receiving antenna, and WT is the transmitted power, WR is the received power. We can observe once it comes out of the antenna, electromagnetic waves comes out in all directions. That you have seen already, guided and unguided waves. In the introductory classes, I have shown you, okay, how the signals radiate, how the waves radiate, the conversion occurs and they get received. This is the transmitting antenna, this is the receiving antenna. This setup we will make use of in order to derive the equation for FRIIS formula. FRIIS, this is the name of the scientist. We have to here assume the lossless and matched antennas. Matched means they are perfectly matched without any losses. Okay, there are no losses here. Whatever transmitted will be received. That is the ideal condition. Let us consider a transmitting and receiving antenna with the apertures AET and AER. Let the transmitter, this part, it will feed a power WT to this antenna. Whatever this terminal is there, to that antenna, transmitter will feed the power WT. And at a distance R, the receiving antenna intercepts some of the power. It will capture some power which is coming out from the transmitting antenna, and it will deliver this captured power to the receiver. Okay, and the captured power, whatever, the received power will be WR. With this setup, we know that the power density or the Poynting vector is given by P equals to E cross H. We will be starting with the basic equation, power density, which is W by A, power radiated per unit area, W by A. From this, we can see W is equal to P into A. So the total power delivered by the transmitting antenna, okay, at the transmitter side, WT is equal to P into A. In general, for specifically transmitting antenna, WT will be PT into aperture is AET. This is equation 1. However, the power density PT, this we have already seen. Power density is equal to W by 4 pi r square. This is what? Area of the sphere. The 4 pi r square. We have seen this in the earlier. You can just check it in while dealing with the beam solid angle. We have seen this. Okay. Power PT, power density, is equal to WT divided by the area, that is 4 pi r square for a sphere. So what we will do, this PT, if there are no losses, this is the power density PT at the transmitting side. And I have told you, we have assumed that there are no losses. So if there is no problem on the communication link, perfectly matched, then this whatever PT will be transmitted, the same amount will be received by the antenna. So PT will be equal to PR, no losses, and it will be the same, WT divided by 4 pi r square. So accordingly, we have this equation WT, which is equal to WR into, just similar to PT into AET, PR into AER. Okay, equation 1 and 2 are from the power density equations. After that, instead of PR, as we have taken this, both are equal, assuming the ideal conditions, no problem on the communication link, no losses, no heat dissipation. So PT and PR are equal. That value we will substitute here. So WR will be equal to PR, that is PR is, from this PT we have got it, WT divided by 4 pi r square into AR. Now, we have already seen the antenna gain. Gain and directivity are sometimes interchangeable terms. However, always the directivity and gain values, how they are related, I think you have already studied this, K into D. Okay. So if GT is the gain of the transmitting antenna, suffix T indicates transmitting side, then by how much amount the receiver power is increased. Gain is what? Output by input is nothing but the gain. How much the received power is increased proportionally, okay, directly proportional. In proportionally, it is given by whatever WR we have got it here. Just a second. Yeah, whatever WR we have got it here, the same WR will be what? Whatever WR has been received, it is gain times that power. It is just like this. Gain is equal to output by input. Okay, this output is your WR. Again into this power fed. This is the power fed because this in turn is equal to PT, right? So output by input. So output will be gain times input. How much amount has been increased proportionally. So this is important. You have to check why it is multiplied by GT, because whatever power is fed, how much amount it has been increased will give you the amount of gain. So this is received power, WR, by the input. Input is this bracket value. Input is equal to GT. But as I have told you, gain is approximately equal to K into D. K, ideal conditions, we have assumed K is equal to 1. So approximately we will equate them. And in the previous session, we have seen the relation between AEM and directivity. So like that, D equals to 4 pi by lambda square into AEM was there. Here we are not considering maximum. In general, it is AE. Okay. Now, according to this, D can be replaced by G because we are approximating D and G. Hence, G is equal to 4 pi by lambda square into transmitting side GT, hence it is AET. If it is GR, then it will become AER. So once G is known to us, you can substitute it here. So WR is equal to, all these parameters are same. Instead of GT, substitute this here. So substituting, I think 4 pi gets cancelled. Remaining is WT, AER, AET divided by R square lambda square. This is the equation. If you simply rearrange, WR by WT, take this to the denominator, WR by WT is equal to remaining all this. This equation which is put in a box, this will give you the relation between the input power and the output power in terms of apertures AET and AER and the distance between the two antennas. This is called the FRIIS transmission formula. It is very simple. We are substituting one equation in the other, assuming ideal conditions. So let me just repeat one more time how we started. We started with this setup, transmitter and receiver. Then these parameters we have AET, AER, then distance is the small r, WT is the power transmitted, WR is the received power. With these conditions, we started with the power density. We know P equals to W by A. So W will be P into A. For transmitter, it is suffixes are TT. Similarly, if you check the receiver, the suffixes are RR. Okay, equation 1 and 2 are similar. However, if there are no losses, this is an equation which you have studied while dealing with the beam angle. There I had told you for a sphere, if you check the power, it is power divided by power flow divided by area. Area is, for a sphere, it is 4 pi r square. So it is PT is equal to WT by 4 pi r square. If there are no losses on the link, PT and PR both will be equal. Whatever transmitted, same will be received. That PR we will substitute here. We will get this. After this, as we want gain, GT is the gain. So gain is equal to output divided by the input. Input is this much. Whatever transmitted will be received. And gain is approximately equal to D. So instead of G, use D. And D is again in turn related to AE. So we have used gain. For the gain, we substituted approximately equal to D. And we have a relation between D and AE. So these three terms we are using. So GT is equal to this much because D and G are equated. Then substituting all these values in this given equation, WR will be this bracket term into GT. GT is D, whatever. For transmitter side, it is suffixes are TT. Just simply cancel the terms and rearrange. The ratio of WR by WT will be equal to this. This is the FRIIS transmission formula. Below you can just observe, I have written here something. If the question is to find the power in terms of gain only, okay, what we have done here, gain we have used, then further gain and directivity we have equated, and as directivity is in terms of AE, we have got apertures in the final equation. Now if the question is to find this WR by WT in terms of gain only, if that is the question for the FRIIS transmission formula, how to continue? This we have already seen. Till this equation 3 we will use as it is. Equation 3 I have written one more time. Here gain and directivity we have equated. So gain is equal to this much. So GT and GR, gain is at the input side, what is the gain? At the output side, what is the gain? GT and GR we have written in a similar way. Once we got these, we will try to get what are these aperture values AET and AER from this equation. What is AET? You check, it is GT into lambda square by 4 pi. Okay. Similarly, AER is GT, let us keep it as it is. Instead of AER, we will substitute AER is equal to lambda square into GR divided by 4 pi. Okay. We will not touch GT because we want power in terms of gain only. GT is already there. Let us try to introduce GR in the equation. How to do that? Using this formula. Similarly, we have written GR, and from this try to find the aperture so that we can substitute for aperture because aperture has GR term. So if you use, this will be your AER. Now substitute this AER in this equation. WR is equal to, this term is same, Instead of AER, I have substituted this and GT is as it is. Now check if any terms gets cancelled. Only take this to the denominator left side. Remaining all, no cancellation. Lambda square GT GR 4 4 16 pi square R square. Okay, this is your FRIIS transmission formula in terms of gains. Okay, this is just an extension, but however, mostly this formula is used in terms of apertures and the distance between the transmitting and receiving antenna. So I hope you have understood this derivation. Any doubts here? Please, you can ask me. You have to understand the figure. That's it. If you remember this figure, you will be able to derive this easily. We started with the power density. We ended with the WR by WT. There is one more small topic. Antenna field zones. Okay, it's just a theoretical part. As you know already, what is a field? Field is some region or the space. Zone, again, field zones. Zones are what? Areas. So for the fields, for particularly antennas, how many fields are there? How we visualize the areas surrounding the antenna, it is about that. The question probably will be, write a short note on antenna field zones. That's it. Nothing more than that. If you observe here, I have drawn a dipole antenna here. Okay, this is the dipole. I think no one has asked the doubts. Any doubts, please, you can ask me. Understood. Okay. So if you observe here, I have drawn a dipole antenna here. This is the feeder line and two poles are there. Surrounding this, I hope it looks like a circle. I have drawn a circle. It's an imaginary boundary. Okay. It is the boundary surrounding the antenna. Inside this boundary, whatever region falls, we call that as antenna region, and there is one more boundary after certain distance. You can observe here a spherical. Okay, as I'm drawing it on the paper, it is looking like a circle. It's actually a spherical, because if you it's a three-dimensional structure, right? Antenna, if you keep it in the space surrounding that, you encircle it with a sphere. Inside that is an antenna region, of course you know it, and at certain distance, and that distance here you can see it, let me just show you, small the capital R. Okay, this distance, with certain distance R, I have drawn one more sphere. Here it is circle, but three-dimensional, it is a sphere. This is also an imaginary boundary. Within these two boundaries, inside this is an antenna region. In between, whatever space is there, that we call it near field region. Near field, that is the field which is near to the antenna. It is near field region. And outside this boundary sphere, whatever region comes, that is far field. Far, the area which falls far from the antenna field. And near field is also called Fresnel region. I think you have studied Fresnel and Fraunhofer, diffraction, all those things. So Fresnel region and Fraunhofer region, the synonyms used for near field and far field. Remember, okay, the same thing. Let me just read it out. Field surrounding the antenna may be divided into two zones: near field, that is Fresnel field, and the far field, Fraunhofer field. These two regions, they are separated by the boundary. As I told you, this outside the boundary, we have the radius R of the sphere, and it is 2L square by lambda. What is L? L is the length, maximum length of this antenna considered. Okay, L is the dimension of the antenna, lambda is the wavelength. Now, the near field is, it is closer to the antenna, and this near field is further divided into two different regions inside the near field only. I am talking about this concentric circle, the remaining part. Okay, this is further divided into two regions. One is reactive near field, the other one is radiating near field. Reactive and radiating. Reactive is a term, this is very much known to you. Reactive, if any other device comes in that particular region of the antenna, it is, the antenna is very much sensitive and reactive. It will simply gives out its power to that particular device which you have kept inside. So that's why it is called reactive near field. And radiating is what, the other side. I am talking about both here in between concentric circle. I am talking about this. Here it is, this is near, this is radiating. This is what, reactive, this is radiating. And it's very important point to be noted. In the near field, whatever electromagnetic waves comes out from the antenna whenever it starts working, it is not completely perpendicular, because you have studied this. Electromagnetic waves, both are E and H are perpendicular to each other. But in the near field zone, they are not completely perpendicular. And there are, in a wave, you have studied about the waves. There are two types of waves, longitudinal and transverse waves. So here in near field, longitudinal component of the E is more dominant. Okay. Now about the far field. In far field, which is totally outside this boundary, this outside the boundary, it is the, here the field components are transverse. In near field, they are longitudinal. Here they are transverse. Okay. Then the power flow is directed radially outwards. That's what, radially outwards, like this. This is about the antenna field zones. There is one more figure here I have drawn. You can just see. Again, antenna I have drawn it. Okay. This is one imaginary sphere I have drawn. If you see these lines, it looks like Earth with these points as poles and these 2 points equators. Okay. If you observe at the poles, see, up and down lines are there. So whatever power or the energy flow is there, up and down, up and down. Okay. These directions show that whenever the energy comes and hits this end, it acts, this pole acts as a reflector. It will change its direction and goes in the opposite direction. This shows that the pole ends are acting as a reflector. Reflection action is taking place. And at the equatorial region, if you check here, if any energy comes out, see here, it is inside. After this boundary, they are radially going outward. Radial, okay, towards its radius, it is coming out like this. The energy flow is in this direction. Okay, this diagram depicts that. Far field, that is coming out, radiated energy flow coming out. Inside, this reflection action is taking place. The same thing I have written here. Enclosing an antenna in an imaginary boundary. Again, I have written a circle. It's actually a sphere with poles and equators I have marked. The region near the poles of the sphere, it acts as a reflector. But the waves which are expanding perpendicular to the dipole, they are in the equatorial region. This results in oscillating energy, oscillating up and down, okay? Oscillating energy flow near the antenna. It is accompanied by the outward flow in the equatorial region. Outward flow, I'll show you. This is the outward flow in the equatorial region, assuming the antenna is omnidirectional, backside. Okay. This reciprocating flow, it is reactive power trapped near the antenna, because the field region is a reactive near field zone. Okay. Reciprocating is what? Up and down direction. So this is about antenna field zones. Basically there are two zones, near field, far field. Near field again is divided into two types, reactive and radiating field. In near field, E and H are not exactly perpendicular, but outside in the far field they both are perpendicular to each other. And if you check the power flow in an imaginary sphere, if you bound it, the antenna, near the poles it acts as a reflector, near the equatorial region, outward flow of the energy or the power. Okay. So I hope you understood today's session. One is we completed radio communication link, FRIIS transmission formula, relation between WT and WR in terms of AE and AR, and the distance small r. And if the question for FRIIS formula is in terms of gain, we have derived that also. And as a short note, this may be asked, write a note on antenna field zones. You have to draw the diagram. You have to mark how many field zones, the areas are there near the antenna. And one more important thing here, inside this boundary, okay, in between these two concentric, whatever fields exist, okay, whatever field exists, it is not very clearly visible. Okay. Once it goes out, after this, you can see the field very clearly. This is very important. In the near field, whatever boundary is there, in the near field, you cannot see, it's not very clear. If I hope it is visible to you here. I have drawn it with a pencil. 1, 2, and one more is 3. This is the pattern, field pattern for this one type of antenna with main lobe and side lobes. In between these two boundaries, whatever field is near field. In the near field, the fields are not very clearly visible to you, but you can analyze the field after this, that is in far field region, in Fraunhofer region, the fields are very understandable. You can visualize it by using the devices. Okay. So this is about these two topics. We'll be having one more topic, that is polarization, linear, circular and elliptical. And we will be solving few problems on FRIIS formula. With that, we'll be completing half of this module. So we'll be continuing these two topics, the problems on FRIIS formula and polarization, in the next session. Any doubts, please you can ask me. Thank you so much.